In this module, we will be learning about properties of charges. Conventionally, electric charges are called positive and negative charges. Like charges repel each other, and unlike charges attract each other. However, if the size of charged bodies is very small, but the distance between them is comparatively larger than their sizes, then such charged bodies are treated as point charges. Coulomb, C, is the SI unit of electric charge. However, smaller units such as microcoulomb and millicoulomb are also used in electrostatics. Electric charge is a scalar quantity which has only magnitude but no direction. Hence, the total charge on the body is equal to the algebraic sum of the individual charges given to it. Let us illustrate this with an example. Consider a body carrying a charge Q1, and we add another charge Q2 to this body. Now, the total charge on the body is the algebraic sum of both charges. That is, total charge Q is equal to Q1 plus Q2. Similarly, if a body carries n number of charges, Q1, Q2, and so on up to Qn, then the total charge on the body Q is equal to Q1 plus Q2 plus Q3 and so on. It is important to note that while adding the charges, proper signs should be used. That is, positive sign for a positive charge and a negative sign for a negative charge. We can determine whether a body is charged positively or negatively by finding the algebraic sum of all charges on the body. For example, if a body is given 5 charges all in Coulomb, say plus 1, minus 2, minus 3, minus 4, plus 5 is equal to minus 3C, which means it is a negatively charged body. Another property of electric charges is that the total charge in an isolated system is always conserved. When a glass rod is rubbed with a silk cloth, then electrons are transferred from the glass rod to the silk cloth. Now, both the glass rod and the silk cloth are charged. Here, there is only a transfer of charge taking place, and neither is a new charge created, nor is any charge destroyed. The number of electrons lost by the glass rod is equal to the number of electrons gained by the silk cloth. If we consider the glass rod and silk cloth as an isolated system, then the total charge of this system before and after rubbing remains the same. Therefore, we can conclude that the total charge of an isolated system is always conserved. We also find that in the natural process, such as the beta decay of a neutron, the charges are conserved, and during the same, the neutron breaks into proton and electron, releasing a neutrino. Here, the neutron and the neutrino are chargeless particles, while the proton and electron are oppositely charged particles whose combined net charge is 0. Hence, we observe that the total charge in this process is conserved, and the charge on an object is measured in an integral multiple of the basic unit of charge that the proton or electron carries and is denoted by E. This property is called quantization of charge. The magnitude of the basic unit of charge, E, is 1.6 into 10 raised to the power 19 Coulomb. In an atom, when we refer to the charge on proton, its value is positive and is referred to as positive E, whereas The value of E for the charge on an electron is negative and is referred to as negative E. Thus, the charge on an object Q is equal to the product of the number of electrons gained or lost by it, N, and the basic unit of charge, E. Now let us calculate the number of electrons 1 Coulomb of negative charge carries. Consider a body possessing a charge Q is equal to minus 1c. Let the number of electrons it has gained to become negatively charged by N, and as the charge Q is quantized, we have Q is equal to Ne, where the basic unit of charge has a magnitude of 1.6 into 10 raised to the power 19 Coulomb, and Q is equal to minus 1c. Substituting the values of Q and E and simplifying, we have N is equal to minus 6.25 multiplied by 10 raised to the power 18. Here, N is a negative integer, indicating that the body has gained a negative charge. So we see that 1 Coulomb of negative charge contains 6.25 multiplied by 10 raised to the power 18 electrons, which is a very large number of electrons. In the practical examples, we have seen, for charging a body, we deal with bodies possessing a charge of few microcoulomb. It is important to note that quantization of charge is significant only in the microscopic sense, when the charge possessed is due to a few hundred times the basic unit of charge E, or even less than that.